Norsat. On behalf of the company, I want to welcome all of you for joining us this morning in our Customizing BUC, the ATOM BUC webinar. I would like to introduce to you our presenter, Michael Schefter, who is the Chief Scientist here at Norsat. Mike is in charge of all research and development activities related to satellite terminals and microwave components. Before we begin, just a few housekeeping items. I encourage you to submit your questions throughout the webinar, and we'll address them. We can stop the presentation and address them, or you can submit them at the very end. We'll also be sending out some poll questions throughout the webinar to gather your feedback. So yeah, without further ado, I will pass things on to Mike.
Good morning, everyone. Thank you for joining us this morning. Today's webinar is on ATOM customization. So it's ATOM is our BUC and SSPA line. And so this is about some of the customizations that we can do. I guess we'll talk a little bit, introduction, we'll talk a little bit about the products, the modular design and how they are suited for customization. And then we'll talk a little bit about 5 different sort of areas where we can do customization, including electrical and RF, mechanical, thermal management, vibration, and then certifications, which often require all 4 of the previous sort of features or capabilities. So firstly, we'll just briefly introduce the ATOM products. There are 3 product lines, 2 KU band product lines, a gas-based series, 20, 40, and 80 watt P1DB, as well as a GaN-based 40 and 80 watt SSPA and BUC. For Ka band, we have a 25 and 50 watt GaN-based product. So the ATOM products, by their design, actually are pretty good in terms of size, weight, and power. They're pretty small, pretty power efficient. However, they're not always the right shape for certain situations. So typically, BUCs are part of a larger system, part of an antenna system, and whether it's an airborne, a land-based comms on the move, some sort of a radar application or a maritime application, there's often sort of changes that need to be made, whether it's electrical, mechanical to fit into a certain area, thermal management or vibration mitigation. So many times in these situations that the standard product isn't quite good enough. So we can make changes to meet those requirements. We have a few sort of standard options, if you will, or standard customizations. The first being the surge protection. So this is input voltage protection over under voltage. It essentially meets MIL standard 704, MIL standard 1275. We also have an EMC EMI option. So this involves a few changes to the product, but it's a standard changes that we can make on all our products. And then the third one is a base plate cooled version. So the standard product is includes fans, but we do have a variation that does not have a fan, but relies on a customer based cold plate or some other cooling solution. So when these options are not, when our standard options or standard customizations are not the solution, we can either modify those options or we can make some new customizations. Okay, so I guess just talk a little bit about the Norsat, BUC design. So Norsat is the designer and manufacturer of all of these BUCs, all of these products. So that includes all the mechanics, all the electrical components, software, and so when we comes to modifying a product, the design for some specific application, it often involves changing multiple parts of it. But because we are the designer, we do know all the changes, we do have all the capabilities to make those changes. The design itself is actually quite well suited for customization. It is, as we said, it's got quite a good size, weight, and power characteristics. It's kind of I call it a stacked design. The the power, the PA portion of it, or SSPA portion of it, is based on kind of modular power modules, we call them, and waveguide combining. The power modules are mounted along the base plate, so most of the heat can be removed through the base plate. And then on top of that, sort of on top of that power module, we stack the other boards. So there's a number of boards required for distribution of power and control to the SSPA. There's a synthesizer. There's an MNC board. There's power supplies. So they're stacked on top of each other, and that leads to a very compact design. It does lead to a specific shape, though, which is not always suited for everyone's application. So the figure on the right, is a representation of our stack design. This is a Ka band system. So in addition to that, when we add input power protection, EMC, EMI filters, we can do three-phase power, fast switching, MNC changes. Sometimes that requires extra boards, and sometimes it requires the BUC to change shape a little bit. The mechanics need to change as well. So we talk a little bit about some of the RF performance and electrical customizations, particularly RF performance. So Norsat uses a wideband MMIC. So instead of using FETs, which tend to be fairly narrow band, all of our SSPAs use a MMIC, which generally is pretty wideband. So we have standard solutions for sort of the low KU, the 12.75 to 13.5, and also the standard KU bands. But we can also do just about anything from about 12.75 to 16.5 gigahertz. So the CDL band, there are some custom radar bands in there that that we can do. For Ka band, typically we can do about 27.5 to 31, maybe slightly more than that. And the modular, the power module, because it is a module, we can add them. We can change the output power, and typically we look at output output P1 dB for GaAs, PSAT or P linear for GaN, and we can tailor the design and make sure that we meet a specific output power in a given frequency band, and also meet all the other typical requirements you need for transmission, gain flatness, phase noise, that sort of thing. So we can do all of that, knowing the output requirements, we can make the output power match that. Related to that, of course, is then sort of an input-output frequency plan. So by this I mean the input IF range and the output power output range. All our synthesizers are programmable. So given a specific input frequency range, with a typical 950 to 1950, we can use that as an input and meet just about any 1 gigahertz range in the frequency bands that we talked about above. But we can also change that, if it wants to 1 gig to 2 gig, or even 2 to 3 gigahertz, we can probably do that within reason, right? It's the synthesizer needs, it does have certain limitations. So as long as it's L band, kinda, it's we can deal with the IF, and as long as we're within our frequency bands, that the MMIC support, then we can pretty much do that. Along with the synthesizer, of course, we would have to probably modify some filters, and as above, we would probably have to look at the SSPA part and make sure that we have the power that's required in that frequency band. So some of the standard customizations I mentioned was this input voltage protection. So it's designed to meet MIL standard 704 and 1275, and it requires an extra board. That's an extra board, a replaced board, as an interface at the DC input. Because of the high currents, typically especially on the higher power BUCs, it does require some active control. So it's not just diodes and it does require some MOSFETs and some control to manage the high currents. The other option that we typically sell is the EMC EMI option. It's designed to meet MIL standard 461, and it does require an extra filter. So this is before the PCB board, or before the DC-DC power supply. We have to add this extra filter board. Also, we have to take our standard DC-DC power supply and replace it with an isolated power supply. And these two changes do in fact mean a mechanical change as well. So the BUC SSPA gets slightly larger. So on the right you can see two diagrams. The top one is it's a 25 watt KA BUC with our standard KA BUC. On the bottom is one with an EMC EMI filter, and you can see there's an extra mechanical layer in there that adds a little bit to the height of the SSPA or the height of the BUC. A couple other electrical customizations we've done. One is fast switching. So typically for radar applications, the challenge here is to manage the current fluctuations, and so when you turn it on, there's a big inrush current, and trying to maintain a fairly constant current between on and off is a bit of a challenge. We've tested it up to 10 kilohertz and different duty cycles, and it works well. Higher the switching, the easier it is to manage the inrush currents, because it doesn't have time to reduce. Another option or another customization that we've done is what we call matched delays. So if you are having an application where you need an SSPA or a BUC that has very repeatable delays, particularly if you're going to power combine outputs, we can design so that the SSPA has almost exactly the same delay through the unit. Requires some very careful builds, matching components and testing and matching and tuning components as we build. And there is to do the fine tuning, there's some integrated delay adjustment, but mostly it has to do with being very careful and matching the components as we do the builds. MNC functions, because we do control or do write all the MNC software, we can implement very specific customer requirements, for specific alarms. The one thing to note is that the BUC constantly monitors for alarms, but does not include a bit built-in test. So while it's constantly monitoring, there is not a way of sort of putting it into a test mode. That is not a feature that it currently has. And then another customization, fairly standard one, is to have an internal frequency reference. We typically use 10 megahertz for KU and 100 megahertz for KA, and the operation or the behavior of this reference we can program. So whether it's uses external and switches if the external is gone, or whether it's always using internal, that information or that operation or behavior can be programmed.
Okay, before we continue, I think we have a poll question to ask the audience. So what custom electrical features are you most interested in? So please select the ones that are applicable to you. Okay, thank you for voting. Mike, please continue.
All right. So the next sort of area that we can do a lot of customization is mechanics. So despite having a pretty small and lightweight BUC, it doesn't always work, and sometimes we need to change it. So we can do a number of things. Size, so we can change the shape. A lot of times people are interested in low profile, so kind of this 1 inch or 1.5 inch high type bucks to fit on on antennas or under antennas, and we can also do different shapes. Another sort of often requirement is the orientation or the mounting. So the BUC can be mounted in different ways, but sometimes you need different mounting options. Weight, particularly on airborne and some comms on the move, or if the BUC is going to be attached to the moving part of an antenna, weight is very important, so we can do some weight reductions. Finish, typically our BUCs are painted, but we can use different paints. We can put special coatings. We can anodize them for better thermal performance. With connectors, we can change connectors. We can move the locations around. A lot of times, in airborne applications, some of the connectors are very specific, to mitigate vibration, that sort of thing. We can split the functionality, so we can separate Upconverter and SSPA into 2 separate units. It tends to make it a little bit bigger in that you end up with 2 units, and you have to have some of the same features in each unit. So instead of having 1 power supply and 1 controller, you end up having 2 controllers and 2 power supplies. The Upconverter power supply being much smaller, but you still need to allow for some space. So there's, while separating, it often makes sense putting the SSPA close to the feed horn or on the antenna, and the Upconverter being away a little bit. It just adds options. It does have some drawbacks, but it certainly adds options to mounting, especially on antennas. And then another mechanical customization is related to thermal. So we'll talk about thermal a little bit more, but heat sinks, base plate designs, airflow requirements, all of those may require some thermal modifications. So I've got a couple examples of some things that we've done, some designs that we've done. So this is a 40-watt KU BUC. It was designed to fit underneath a comms on the move terminal. So it's I think that's a 40 centimeter or 45 centimeter comms on the move terminal. In this case, the BUC is on the right-hand side under the terminal, and on the left-hand side is some control circuitry and a small modem. You can see that besides changing the shape to be a low profile, the thermal changed quite a bit. So normally we would have the fans on the bottom taking heat away from the power modules. In this case, to make it low profile, we needed to spread it out and make it flat. So we had to change how the heat pipes on the bottom of the base plate are used to pull heat away from the SSPA portion and move it over to the fans where they can be where the heat can be dissipated. Related to that, and a very similar design, were these sort of additional designs that were generated. So these are also 40-watt BUCs. Same basic concept as the previous one, but they had different requirements. So the one on the top left, actually very similar to the first one that you saw, except the requirement was that the airflow had to come from the end. So there was some redesign required to ensure that we had the airflow coming from the end the way the customer required it, because of the location it was going to be mounted in. The other models that you see relate to the output of the waveguide. So there was a couple of things. There were some connector changes, but also the requirement was the waveguide was to enter or was to exit from the top of the BUC because of the way it was going to be mounted in this application. A few other things. We've done some work where we've separated the BUC and the SSPA. You can see that on the sort of the top left. You can see on the right, it's a sort of a top-down view of the 25-watt KA, sort of showing some of the boards inside. The bottom left is it's, instead of going separating functionality, this one has a combined functionality. So we have both a KU and a KA SSPA in a single enclosure, also designed as a low-profile enclosure. And then the product on the right is a 25-watt KA SSPA designed for Airborne. In fact, these are all designed for Airborne. And this one is it's quite small. It's been weight relieved, has custom connectors, custom coatings. So it's quite a custom buck. The insides, the basic power modules and power combining are the same, but probably almost every other board in there has changed.
Okay, before we continue, we have another poll, so please deploy out. Which mechanical customization are you most interested in? So please vote and choose the ones that most apply to you. Okay, great. Thank you so much. And Mike, passing things on back to you.
Okay, so thermal management. Thermal management is very, very important to our BUCs and SSPA. The mimics, SSPA portion generates a lot of heat, and we do have to remove that heat to basically to ensure RF performance. Heat will degrade RF performance, but also to protect the BUC and ensure that it meets its lifetime longevity as well as MTBF. The BUC power modules, the power SSPA portion, is all mounted directly on this base plate, which in the picture, the top picture is kind of in the center, and the bottom picture there, it's on the bottom. 90% of the heat is removed by the base plate. It's the second largest component is the power supply. Even though the power supply is about 93% efficient, when you've got 300 watts of power that you're using, you're still going to generate 20, 21 watts of excess heat, right? So our standard is the top picture, these integrated fans. The base plate is configured or is designed with heat pipes and a radiator, and the fans are then blow air across the radiator. Our standard temperature range is -40 to +60, and we can certainly extend that to +70 to meet some specific requirements. Specifically, some of the airborne emergency short-term temperature requirements. We can adjust the temperature up a little bit, but it's not expected to run at those temperatures. It's running for a short period of time is okay, but not long-term operation. The second option, and this is something that we have in as a standard product, is what we call our base plate cooled. So this is essentially the same electronics, except that the heat pipes and the radiator are removed, and we have just a flat base plate. The base plate may or may not have heat pipes in it, and some of that will depend on the cold plate that we will integrate with. So in this case, we're expecting the customer or the mounting solution to have a cold plate, and we can modify the base plate to move heat around to best work with that cold plate. Sometimes they have certain spots where they need to be mechanically. It doesn't always mount properly, so we can move the heat around a little bit to make sure that we integrate with the cold plate. And we typically want the base plate to be maintained at about 70 degrees Celsius. Despite all of this, we do continually monitor the internal temperatures, and if they do get too hot, we will shut the BUC down. That's just sort of a safety, a product safety feature. That internal threshold we can adjust. It's software adjustable. So if you need to have some mode where you need to have it go hotter and you don't want to shut it down, we can allow that, but it will impact MTBF. So to give an idea, this is a table just showing some power dissipation in sort of the various BUCs. So what I circled there, not very well, I guess, but what I circled was a 80-watt gas BUC. So we know that with a fan-cooled version, the total power requirement I think is about 440 watts, and we know that the thermal power dissipated on the base plate is about 380 watts, and then the rest of the power or the rest of the heat is dissipated through the body. Most of that being on the top where the power supply is, but because it's aluminum, it does dissipate throughout the body of the unit. So sometimes these standard solutions, both our fan and base plate solution, they're maybe not sufficient. Particularly if there is no really good cold plate for use, or there may not be a solution. So we might need to do some modifications to make it better. So some examples might be in an airborne unpressurized application, some comms on the move can be have quite a bit of heat requirements. In maritime terminals, because maritime equipment is in a radome, it doesn't really get rid of heat very well unless you put an air conditioner with it. So especially on smaller terminals where there's not a lot of space, we can see some elevated temperatures. So how do we work with this? So we do a couple of things. So typically we need to work with the customer and the requirements to try to understand what the requirements are, and then to work out a solution. So we can use some high altitude fans. There are some fans available that they turn very fast and they move a lot of air, and they at altitude they don't move as much air, but they still move sufficient air to provide good airflow and some thermal dissipation. Of course, when there's less air, that transfer of heat is less, so you have to move a lot of air to make this work. We can also modify our base plates and add base plates, right? So add heat sinks as well. So in the picture in the middle, this is an 80-watt gas BUC that we modified for high altitude operation. So this was for 50,000 feet. We modified the base plate with a different heat sink. We have a very high velocity fan that works at altitude, and then on the power supply, which is on the top, we also added a heat sink and added some additional fans. So this was a design that there was no cold plate that was available, and so in order to make this work, we had to come up with some quite extreme airflow solutions. We also, because we had to add size to this, the top heat sink is additional size. The bottom is about the same as the previous heat sink, but we did add some to the top. We do have to work and make sure that mechanically it fits where it's supposed to. So that was a high altitude design. The design on the right is a fanless design using fractal heat sinks. So in this case, the requirement was to meet 70 degrees Celsius with no fans. So this design does that, and because there's no fans, it starts to it does have convection. So as it heats up, there is some airflow movement, but a lot of it is radiation, and so you'll notice that it's anodized because the anodized provides a better with radiation, it provides a better solution. So how do we do this? We do analyze the requirements. We do a lot of simulations. We have a fluid dynamics finite element analysis software set. So we do a lot of iterative solution or iterative simulations. We can look at thermal contours, airflow, pressure drops, that sort of thing. So doing that, then we can make mods, mechanical mods in in our mechanical design software, and eventually come up with a theoretical solution, and then we would normally build it and then test it. So we have in-house temperature chambers. We have temperature probes and data loggers, IR cameras. So it becomes a bit of an iterative process. Generally, we can get pretty close with the theory, and so the verification or the testing is usually a verification that it worked rather than a part of the design cycle.
Okay, so before we continue, we have another poll. Which thermal management issues are you currently experiencing? So please select the ones that are relevant to you, please. Okay, Mike, passing things back to you.
Okay, thank you. Okay, so another large area where customization is required is by vibration mitigation. So the vibration shock requirements, particularly for airborne, maritime, comms on the move applications, can be quite extreme. And the exact profiles, the vibration profiles, will depend a lot on the type of vehicle, and even given the type of vehicle, there's, for aircraft, for example, is it a rotary wing, propeller, jet? Is it a vehicle? Is it a wheeled vehicle or a tracked vehicle? The location of the BUC or the terminal in the vehicle will make a difference. The application makes a difference. Is it a commercial or military? Is it designed for paved roads versus unpaved roads, that sort of thing. Also, whether there are operational vibrations as well as shock or as well as survival. So there's a lot of different requirements, and they change quite a bit depending on what the application is. Most of the time, the standards that are used or that are called up are the RTCA DO160, which is an airborne spec, MIL standard 810 for most land-based, but also some airborne and some Navy applications, and then MIL standard 167 and 904. So those are maritime shock and vibration. They're typically meant for the system as a whole, so not just the BUC, but the whole antenna system. And despite there being all these standards, there's a lot of customization or tailoring, I should say, of the vibration profile. So that can be because of specific requirements for this particular application. It could be because of the way it's mounted, because of some additional capabilities that it needs to have or to mitigate against. So again, those are the kind of the standards that are used, but there's a lot of tailoring required to get the real requirements. So with our standard product, we do have some vibration mitigation. So the synthesizer has a vibration tolerant reference on it. The PLL design, adjusting loop bandwidths and such, we can try to design it so that it's somewhat tolerant. We can look at the different vibration profiles and try to move the loop bandwidths around a little bit so that we can get the best design or the best mitigation. And then the synthesizer itself has a vibration dampening mount. So internally to the BUC, the synthesizer is not solidly mounted. It is mounted on vibration dampening mounts. However, what we found is that despite our, sort of our internal mitigation, to meet some of the more extreme vibration requirements, we do need some sort of an external vibration dampening assembly. Now, this can be part of the BUC mounting assembly, or sometimes the antenna itself has its own vibration dampening because other parts of the antenna also need it. And so, we need to understand: do we need an assembly for the BUC itself? Is it part of the antenna? Do we need something special? And even if the antenna system has has vibration dampening, how does that affect the vibration? How does that get transferred to the BUC? So there's some analysis that needs to be done to understand what modifications, if any, we need. And then I guess a caution is that these unfortunately external vibration assemblies, because they end up with the BUC moving, they're not very well suited for cold plate applications. Cold plate applications require that the BUC be mounted fairly solidly to the cold plate so you can transfer heat through the base plate. But with a vibration assembly on the BUC, that's not possible. So it really doesn't work well with a vibration assembly between the BUC and a cold plate. So a lot of times the cold plate will have its own vibration dampening. And so part of that there is some design effort required. So providing weights and center of gravity and center of mass, as well as mounting locations and such, can be used to ensure that the BUC is mounted properly on a cold plate that's already has vibration dampening. So a couple examples. The two that you see are designs that have been done. The first one is a 25-watt KA BUC with an external vibration. So it's basically a plate with the vibration dampening mounts. We choose the mounts based on the profiles as well as the size and weight of the BUC, including the number of mounts. So these are we have the one on the top is a pretty standard design. It's something that it can be used fairly easily. It can certainly be modified. If the mounting position is in the wrong place, we can make some changes to that. But it's a fairly standard design for us. But we would need to analyze the requirements and then come up with the vibration assembly or the vibration mitigation assembly. And then once we've done that, we would do some design and then verify, build, and test it. So typically when we test, we're looking at phase noise, integrated phase noise, or bit error rate. Bit error rate being one of the best solutions. Typically there will be some degradation. So we need to understand what system margin there might be for vibration. There's usually a little bit of degradation in bit error rate, but ultimately bit error rate, at least on a communication system, but bit error rate is the important parameter. Phase noise, which is essentially jitter, can be mitigated, or it may look bad on a plot, but it may not really make much difference in terms of a bit error rate measurement. The picture on the bottom right, is an external vibration assembly that was designed for unmanned airborne vehicle. It's a 80-watt BUC. So it's a similar kind of design to the one above. It's a plate with a number of vibration dampening mounts that were chosen based on the size, weight, and profile of the vibration requirements.
So we have another poll. Do you have applications requiring vibration or shock mitigation? So please select one, yes or no. Okay, thank you. And passing things back to you, Mike.
Okay, so the last area that we'll talk about is, I've called it certifications. And we kind of touched on some of the, it's kind of an amalgamation of the previous modifications. To meet some of these requirements requires electrical, mechanical, and sometimes some optional features to be compliant. So Norsat does have some what we call our standard options for MIL standard 704 and 1275, also which are input voltage standards, 704 being airborne, 1275 being land-based. MIL standard 461, which is EMC, EMI, we have standard filters that are designed to meet that. And then RTCA DO160 has a number of different requirements. So we have some standard products or standard options to meet some of those, particularly the EMC, EMI, some of the ESD and lightning and voltage protection. But there is some overlap between the first three, the MIL standards and the DO160. They're not exactly the same, but oftentimes, if you can meet the MIL standards, the DO160s are, you can use them as an alternate, essentially. However, these standards contain many different levels, profiles, and requirements depending on what application you're actually doing. So whether it's land, airborne, Navy, depending on the vehicle, and depending on how it's going to be used. Is it is it meant for operational use, or is it a highly robust system, in which case it may have more requirements than if it's just something that doesn't need to be available all the time. So Norsat has designed boards and options and filters to meet these requirements, but we certainly haven't tested to all products, haven't tested all products and all variations of this. There would be just too much to do. So what we do have is a number of designs for each product, and the designs, each product line, the designs are very similar. So using those similar designs, and we can use a very the designs for one system can be used in another system with very low risk that that it would fail. However, we can also, if needed, we can also do third-party testing for each of the certifications. This can be expensive and time-consuming, and depending on the requirements, we may be able to use similarity to reduce the risk enough to not have to do it. And this is especially true if the system, or at the system level, the similar testing is going to be done. So for example, if they're going to test MIL standard 461 at the system level, it may not be necessary to get a full certification on MIL standard, on the BUC MIL standard 461. It may be sufficient to know that the system has options, variations, filters built into it to meet that requirement, and that it may not be required to get a full certification on the BUC itself if the system is going to have a certification. So let's talk a little bit more about this input voltage. As I mentioned, there's two. There's the 1275, which is a 24-volt ground-based, and then there's the MIL standard 704, the 28-volt. I should say that there are actually some different voltages in those standards, but those are the two voltage profiles that we've tested to. Typically, there's normal, abnormal, and emergency voltage levels, and then on top of that, you end up with voltage surges and spikes. So how do we mitigate it? Well, we need to add an input voltage protection filter. So on all our BUCs, we do have this interface board that does have some protection on it, but to meet these standards, we replace that board with a board that has much more protections. And sometimes we have to add some active features. So the BUCs typically have a pretty high current, and especially when you get into them at the lower voltage ranges for abnormal or emergency voltage, you end up with very high currents. And in order to protect against the voltage surges and spikes at these lower voltage levels, you do need active controls, basically, MOSFETs to control both voltage and, also big enough to handle the current. And in order to meet, this requirement, we do need to use our option P, which is what we call our surge protection. So you can see, we've done this table at the very bottom. It sort of explains a little bit of what we've tested. When we say C, which stands in this case is compliance, so we've done full testing of that unit. When we talk about design, it means that we've designed boards and options and maybe done some testing, but it's not been fully certified. And then where it says N, it means that we would need to do some additional work. It would mean taking a board that we have and maybe adjusting it or modifying it to handle higher currents or to meet certain requirements. So EMC, EMI, primarily MIL standard 461, but the DO160 standard also has some EMC, EMI requirements in it. They are similar to MIL standard 461, although not identical. Typically, it's radiated and conducted emissions, radiated and conducted susceptibility, and ESD. And in the case of the DO160, there's also lightning. Mitigation, we use an isolated power supply. We have an additional EMC, EMI filter, which in many cases requires some mechanical mods to use. And then there's also the basic design of the BUC. The grounding is internal grounding is also very important. The BUC chassis is ground, but we don't want any currents flowing through the chassis. So internally, there's always returns for all of the voltage sources. There's an equal return so that we don't have any volt or any currents flowing through the chassis. And the challenges, of course, are high current. So the typical voltages that we're using are 24 to 48 volts, and with high power devices, drawing 400 watts of power, 48 volts, it's still a lot of current. And so designing filters to handle that kind of current can be a challenge. The other challenge is that these specs require or use an inductive source. It's quite a large inductive source, and that causes a lot of issues with oscillation and feedback unless you have enough capacitance at the input to sort of damp that out. So that's another requirement. There's we do have to add some capacitance, which unfortunately also adds to the inrush as it charges up. So an example of some of the EMC EMI testing. We've done some testing for some airborne requirements, so some of the airborne standards or the airborne profiles, I should say, as well as some land-based profiles. And as it is a standard option, we use an option F, which stands for filter, to provide this protection for EMC EMI. So environmental. So there are two standards that we typically look at: MIL standard 810 and the DO160. As we said before, there are the MIL standard 810 has 28 different tests or methods, as they call them, and each one of those has at least one or more procedures, which are variations of the test. It covers everything from altitude and temperature to shock, vibration, even contamination by fluids, explosive environment. It covers a wide range of of characteristics, and in most cases they expect there be some tailoring. So you might not need exactly what's in the standard, or you may set the temperature limits to be higher than what's in the standard, and just use the methodology to do the testing. So with this the mitigation of this, it's mostly mechanical. Most of what's in MIL standard 810 is a mechanical modification or mechanical design. Not all of it. Sometimes to meet temperature, there might be some different electrical performance designs that have to be made. But then, to make sure that it's working, you pretty much have to test everything. So, we can test internally using some calibrated test chambers, vibration. We have a vibration table. But if you need third-party testing, then we have to go out to an accredited lab. Sometimes you can get away with sample testing, like for example, contamination by fluids or salt fog. We can use samples instead of using the whole product. And then, what are the main challenges? Vibration and shock are typically challenging, and high altitude is also a challenge, especially for the thermal management. So some of the testing that we've done, high-low temperatures, rain, humidity, some salt fog. We've also done some contamination by fluids. And then the last certification that we'll talk about is Airborne. It's kind of a combination of the DO-160 is just an airborne application. MIL standard 461, 704, 810. They have portions of them that are related to airborne. So there would be parts of them that we would have to deal with. DO-160 has, I think, 26 sections. Each of those have different variants depending on the type of aircraft, the application, the location of the equipment in the aircraft. And it really does cover a very similar range of tests to MIL standard 461 and MIL standard 810, from altitude, humidity, vibration, shock, all the way to EMC, ESD, and lightning. So it's quite a comprehensive standard. And of course, we haven't tested all of it. We've tested some of the more common sections. How do you mitigate? As before, it requires a combination of mechanical and electrical modifications and testing. And as before, the challenges tend to be vibration and thermal. So some of the sections, some of the testing that we have done for for the DO-160 is shown here. And then I guess there's
we have two more polls. The first one is, what certifications are you most interested in? So please select the ones that apply to you. And then we have one more. What applications are you most interested in? So also please select ones that apply to you. Also, just a reminder, if you have any questions, please submit them. You can always reach out to us, at the end of this webinar, or reach out to Mike if you have any other specific questions that were not addressed in this webinar today. Okay, Mike, yeah, passing things back to you.
Okay, so I guess for a little bit more information, there's a few case studies and white papers on our website that might add a little bit more information. We did do a custom SSPA for NASA, which was a high altitude unmanned aerial vehicle. I added this comparison of GAN versus GaAs. GAN, the two devices behave quite differently. The GAN can be quite efficient, so it has some benefits, particularly at high altitude where it has to mitigate thermal much better. Because being more efficient, there's less heat to get rid of, so there's some advantages. And then there's a kind of a discussion of thermal management on a white paper on the future of thermal management. So that is the end of the presentation, and I guess we're open to any questions. Thank you.
Yeah, so we have a few more minutes. I don't see any questions coming through. Yeah, as I mentioned, if you have any questions that were not addressed today, feel free to reach out directly to us at marcom@norsat.com. We can, forward the questions to Mike and he can get back to you. Also, just a reminder that we do have these webinars on a monthly basis, so please go to our website, www.norsat.com/webinar to see our calendar of events that we have coming up. Also, we are participating in a few upcoming virtual trade shows, including the Naugus trade show at the end of August, and also the Communicate Asia virtual trade show that's happening in Singapore in September. So please visit our website to just check out the roster of events that we have. So if there's no more questions, I will conclude today's webinar, and I want to thank each and every one of you for taking the time to join us today. And thank you, Mike, for the wonderful presentation.
Thank you, everybody.